Good morning, good afternoon, and good evening to everyone joining us. First, I would like to personally welcome all attendees and speakers to this first webinar on modern technologies in disaster management. My name is Tamelo Makati, and I'm an intern at the UN Environment Program under the Resilience to Disasters and Conflicts Global Support Branch. It is my pleasure to welcome you to our webinar series, Modern Technologies in Disaster Management. The series is divided into 4 parts, being robotics, AI, drones, and Internet of Things. We'll have the chance to learn from and engage with leading experts from around the world as they discuss opportunities and challenges associated with these technologies and their use in disaster management. Today, we are launching the first webinar on robotics for disaster management. Before I go on, some housekeeping rules. Please make sure that you have all your cameras off and you are muted so that doesn't interrupt our speakers. We have 5 speakers with us today who will take us through that presentation. But first, we will start with opening remarks from our acting head, Dr. Muli Tumarukudi. Dr. Muli is currently the acting head of the Resilience to Disasters and Conflicts Global Support Branch of the UN Environment Program. He holds a PhD in environmental engineering, and since joining UN Environment Program in 2003, Muli has been involved in dealing with environmental issues and crisis responses in all major disasters and conflicts. This includes in Afghanistan, Iraq, Lebanon, and Syria. He has also dealt with environmental issues caused by tsunamis, floods, earthquakes, volcanoes, and oil spills. With more than 25 years of international experience in the field of environmental management in crisis situations, Muli is one of the world's leading authorities on this topic. It is a pleasure to have you with us. I will now pass the floor to you to give us the opening remarks. Thank you.
Thank you, Clamelo, for your kind words of introduction. And it's indeed a pleasure to open this very first international webinar on modern technologies for disaster management. As Clamelo mentioned, I have been in the field of disaster management for over 25 years. And I have seen the entire range of disasters, be it floods, earthquakes, landslides, tsunamis, volcanoes, also industrial accidents, oil spills, chemical spills, factories. Now, over the last 20 years, we have been following up on this incident, and we also been noticing that new technology is coming to the aid of disaster management. Drones, for example, which are barely coming into existence in 2010s, have now become ubiquitous. It's invaluable assistance tool. I can see Internet of Things taking up that position very soon, that we would know about oil spills or industrial accidents much before we get a satellite image of that. We also see the huge potential of artificial intelligence in disaster management. And when I talk about disaster management, it is not just about response. It's also about predictive intelligence. It's also about early warning. So we thought at the United Nations that we should think in what way the new generation technologies can be leveraged for disaster management, which include prevention of disasters, most of all, but also effective early warning, emergency response, and recovery actions. With this in mind, we have initiated a project where, first of all, we are currently doing a global market scan of available technologies and good applications. We are looking at research projects going around the world on these topics. And in another 6 months, we plan to do a global hackathon on this topic, on how new technologies can be leveraged for disaster management. And with that in mind, we then plan to engage with international research community on the areas where we need progress, and also the private sector who is already doing work to make it more broader, and also manufacturers who are making new technologies but not necessarily engaged in disaster management areas to expand their areas into disaster management as well. We have a big ambition in mind, and we are also partnering with the International Telecommunication Union, World Meteorological Organization, UN Office for Disaster Risk Reduction, among others, so that the application of new technologies for disaster risk reduction become more global and more universal. I'm extremely delighted to see that we have an excellent lineup of speakers today. I was talking to Dr. Lee, who mentioned that he did his PhD in 1985 talking about robots. So we have real stalwarts in the session today, and I'm looking forward to the session. Thank you for all those who are working on this session and also behind the scene. Thank you. Back to you.
Thank you so much, Mali, for setting the stage of today's webinar and for emphasizing the importance of modern technologies in disaster management in today's vulnerable world. So before we start with the presentation of the speakers, we'll also have opening remarks from Dr. Chase Lee. He's the director of the ITU Telecommunications Standardization Bureau. Dr. Lee has contributed to ICT standardization for over 30 years, specializing in areas such as integrated services, digital networks, global information infrastructure, and internet protocol. He was a researcher at Korea Telecom and took up a role at the Electronics and Telecommunication Research Institute in Korea. And he worked at the Korea Advanced Institute of Science and Technology. He was also a senior advisor to Korea's Ministry of Science, ICT, and Future Planning. Within ITU, Dr. Lee served as chairman of the ITU Focus Group on Next Generation Networks, as vice chairman of the ITU Focus Group on Internet Protocol Television, and as the vice chairman and later chairman of the ITU-T Study Group 13, which works on future networks and cloud. Dr. Lee, we are truly delighted to have you with us today. I will now pass down the floor to you.
Yes, thank you very much, Makati. So colleagues and friends, I hope you and your families are all in good health and good spirits. It is a great pleasure to voice my support for this new series of UN environment webinars. And I thank you for the kind invitation to address you today. As Murali said, I come from a tech side, ICT side, having robotics as a master grade in 1985. I'm very happy to join you with this important event. Robotics are quite well advanced, that such advances in robotics are closely intertwined with advances in many fields, such as AI, Internet of Things, high precision tactile connectivity that we will achieve through 5G and beyond. The field of disaster robotics has gained recognition for its promise of delivering adequate responses in the event of emergencies. So disaster robots can be deployed in place of human operators to perform mitigating actions in the harsh environments, to conduct rescue operations, and predict future damage. As we are entering these new frontiers in technology and new frontiers in humanitarian action, and as we continue to achieve advances in collaboration, each step forward is propelled by a diverse set of expertise. That's exactly why the Sustainable Development Goals emphasize the importance of partnerships. And that's exactly why ITU is working to be a valuable partner to everyone innovating with ICTs. This commitment to collaboration is a commitment we share with UN Environment. Together, ITU, UN Environment, and the World Meteorological Organization are supporting the focus group on AI for natural disaster management. Our partnership has helped us to convene a diverse set of highly dedicated experts. This focus group is open to all interested experts. So I would very much encourage you to join this work. We are calling for the contributions of as many stakeholders as possible to ensure that we build on firm foundations when developing new IT standards for natural hazard and disaster management. Inclusive dialogue continues to grow in importance as digital transformation accelerates. IQ is the UN Special Agency for ICTs, and ICTs are key to the future of all industries and public sector bodies. So with 193 member states and over 900 academia and private sector members, we continue to bring together experts in different fields to learn from one another and coordinate convergence. I believe this webinar is another moment to learn together. Having simulated inclusive dialogue for many years, we have created the coordinations necessary for IQ to deliver influential standards in fields from transportation and energy to financial services, cybersecurity, climate change, healthcare, and smarter cities. So inclusive dialogue has also been foundational to IQ standardization work on frontier technologies like AI, quantum information technologies, blockchain, possibly robots. Being inclusive of all possible perspectives is essential in clarifying the contributions expected of all stakeholders, including the contribution expected of IQ standardization. The IQ community will follow this new series of UN environment webinars with great interest. So I'd like to once again take this opportunity to thank Dr. Murali for your kind invitation today and for your leadership in the focus group on AI for natural disaster management. We know from experience, such meetings of minds can lead to the new directions in innovation and the new partnerships necessary to address the greatest challenge facing humanity. So I wish all the good result of this webinar. Thank you very much. The floor back to you.
Many thanks for these opening remarks, Dr. Lee. As we move forward, we will hear the practical applications of robotics in different stages of natural disasters. And at the end, we have allocated some time for discussions and Q&A session. We'll now have our first speaker, Dr. Ali Akbar Agam Mohammed. Dr. Ali is a robotics technologist and group leader at NASA JPL's Autonomous and Robotics System Division and Caltech's Center for Autonomous Systems and Technologies. Dr. Ali's research centers on autonomy and AI for robotic systems with a dual focus on planetary exploration and terrestrial application. At JPL, he leads the team COSTA and the development of Nebula autonomy solution for search and rescue and disaster response mission. Previously, Dr. Ali was with Qualcomm Research leading the perception efforts for self-flying drones and autonomous cars. Once again, welcome and thank you for joining us. Over to you, Dr. Ali.
Thank you very much, Tamelo, and thanks for the invitation. It's a great pleasure to be part of this event. Let me share my screen. Let me put it in full screen mode. Can you confirm if you can see my screen and the right part of the presentation?
Yes, we can see it.
Awesome, perfect. Okay, so my talk is going to be focused on robotic AI and autonomy for search and rescue applications. Basically, from robotics perspective, when we look at search and rescue, there are certain metrics or evaluation parameters that we want to look into and focus on. Some of these include coverage, how much of the environment we can cover, what parts of it, in what speed, what's the endurance of our robotic systems that are exploring this environment. what's the safety parameters, safety of the survivors, rescue team, as well as the robots themselves. How fast and with what bandwidth we can communicate the data we are gathering with the team of the management who are basically pushing the full operation forward, and how intuitive and easy is the interaction for some personnel that are not necessarily trained as roboticists. So I kind of I skipped the part that to go in the details of the previous missions and in search and rescue, and directly we'll go into kind of the technology and robotic AI. Basically, if you think about the mission being search and rescue and metrics being things like coverage, speed, and in robotics, the technology, you can divide it to two pieces. Robot body, what's the mechanical, electronics, the hardware, the locomotion system, and robot brain, AI, and autonomy. So in my talk, I'll mostly focus on the top part, robot brain, AI, and autonomy, because as far as I understand, the other speakers are going to cover very well the robot body part. And in part one, I'll briefly go over one example mission to just as a context for the technologies I'm going to talk about. And in part two, I'll just touch very briefly on some pillars and components of robotic AI that would be most related to search and rescue missions. Okay, as a reference mission, I'm focusing on DARPA Subterranean Challenge, a huge project, huge effort started in the US 4 years ago with participants from all over the world. The goal of this robotic event, which is held as a competition, is to autonomously explore unknown environments, as the ones that you can see here. Pretty challenging environments, man-made mines and tunnels after disasters, urban structures that are abandoned, or they're basically, we need to search and explore and gather information, natural caves, and environments that combines all these features together. So a feature of these environments is that they're GPS denied, communication is really difficult, and mobility-wise, it's difficult to explore these environments. But even further, operationally, they introduce more challenges. We need to cover multiple kilometers in only 1 hour with no prior map about the environment, and with no human who is allowed to enter the course in this competition. There's only one single external supervisor who can see the data coming from robots, if there is any data coming when communication is established. And most importantly, there's only one chance to operate the system. And this is really important because the structure of this competition is done such that it pushes the teams beyond their research and have something closer to a product, so that only in that 1 hour you can deploy and see the results. It's not like a research that you can go, and if something doesn't work, you come back and fix it. But you work 4 years, and the only chance you get is 1 hour to demonstrate if the system can actually explore these environments and collect the necessary information. The technologies developed towards this effort are evaluated by finding certain targets that are distributed in this environment. We get 1 point per target if they're detected and classified correctly. If you exactly detect where it is in the global coordinate with less than 5 meter error, and somehow in that 1 hour report it to the surface. These objects have features, as you see in the bottom right, that basically try to represent a presence of a survivor. Things like acoustic, audio, gas, thermal measurements like temperature variation, and visual and Wi-Fi, like a cell phone of a survivor and so on. There has been more than 50 institutions participating in this effort in the last 4 years. So this has been a really amazing push for technology towards search and rescue. Of course, the effort is still simpler than a real disaster robotics, real world disaster robotics scenario, but it's a first step. It's a great step towards that. As you can see, there has been more than 20 different UAVs deployed in this effort so far, more than 60 different ground robots, legged, wheel, tracked, and so on, and even one beam has been deployed. And this gives really a plethora of technologies to study and see, what works, what doesn't work, and how, we can combine these to push the envelope forward. So our team is called CoStar, and it's a collaboration between NASA's JPL, Caltech, MIT, KAIST, Lulia, as well as a lot of industry partners. We have been able to do well in the last competition and won the final effort, the latest, I should say, the latest competition so far, which was in urban search and rescue back in February 2020. Our concept of operation relies on multiple robots with heterogeneous capabilities. So we have legged robots, wheeled drones, tracked robots, that each one is dispatched to part of the environment autonomously. They try to understand what is needed locomotion-wise, AI-wise, and dispatch themselves to be able to explore and maximize the coverage in the limited amount of time that we have. So you see pictures of some of the robots we have deployed. And as I mentioned, these complementary capabilities get dispatched to different parts of the course, closer to the base station where the robots being launched. We try to drop communication nodes like breadcrumbs to create a wireless mesh network to maximize the bandwidth and the ability to talk to the surface. But after a while, as you see here in the shaded green, the robots are fully autonomous on their own and exploring the environment and come back to the surface to return the data they're gathering. Just in terms of numbers, to give you a sense of the practice in our team, we started back in 2018 with 1 or 2 robots, a very minimal exploration capability, 200, 300 meters. But in the course of 2-3 years, now our latest operations, we have been able to deploy 11 heterogeneous robots simultaneously, autonomously exploring the environment. Per robot, the system is able to explore more than 2 kilometers in 1 hour over complex terrains and map more than 4 kilometers. So I did talk a little bit about the mission. In the next few minutes, I will touch very briefly over some of the technologies that is basically our pillars under these behaviors that I talked about. Of course, if there are interests, please reach out to me offline and we can go deeper in these technologies because there's not enough time at this point to cover those. But I'll go over briefly, touch on each one of them for 30 seconds or so. So the first technology I want to touch on is traversability. So we have been working a lot on traversability efforts. So here on the right, you see a mine where we have a collapsed part of mine, and the robots goes and starts basically evaluating what trajectories I can take to explore this part and search for signs of survivors like CO, the gas or thermal or so on under the rocks. And this has been a big part of our efforts to evaluate where is it traversable, where is not, and make sure the robot can handle these sorts of environments in this level of extreme cases. In the right, you see similar effort on the ground robot, wheeled robots, where it's 900 feet underground in a coal mine that the robot's trying to explore really extreme environments. And when a wheeled robot is not able to do so, as you see, it stops here. It autonomously dispatches the tracked robot to traverse certain parts of the course, or if there are elements that needs legged platform, the system sends a legged platform to explore those. The second technology is navigation, where we are trying to handle GPS nav, variable lighting, dust, fog, smoke.
Sorry, Dr. Ali, sorry to interrupt you. Can you wrap up in a minute?
Sure, I'll wrap up in a minute very quickly. So as you see, we have a lot of different sensors that we combine to handle different parts of the course. I'll move on. The next technology is on mapping, where we are trying to create large maps to basically pinpoint the findings in the environment and inform the operators that where the events are happening. Communication between robots is a key aspect to send the data. As you see here, we are showing how we drop the communication nodes in the environment to create the wireless mesh network, and sometimes robots act as mobile nodes so that we could act like repeaters, that we basically still can talk to the robots that are deeper in the environment with maximum bandwidth possible. Coverage, of course, is an important part where we search to the artifacts that I talked about on the bottom left. So I'll skip this slide and move on to the intuitive user interface, where we check the health of the system, and the operation team is able to see where each robot is, what the health is, and how mission is progressing at the moment. So with that, this is a very brief touch on this particular mission, which is a step again towards pushing the technologies on the search and rescue forward. And with that, I'll briefly conclude kind of summarize the main points of the talk. One being that when we analyze the technologies or robotics-related technologies for search and rescue, it's important to look at robot brain and robot body in harmony and together, to understand what the state of practice and state of the art there is. Assisted AI and autonomy can help a lot. For each given robot body, having a better AI and autonomy will open a lot of opportunities on how we use these systems. New investments, recent investments from different sectors, commercial sectors, government, have been pushing the envelope in this front and are a step towards basically increasing trust in putting these technologies forward. And finally, under the hood of all we do, really the main element is the fact that we are trying to predict uncertainty and quantify the risk to be able to increase the trust in basically the system to be able to reliably deploy it. With that, that's my final slide, and I want to highlight this is, of course, the work of a massive team, more than 100 people at different institutions for the last 4 or 5 years. Thank you.
Thank you so much, Dr. Ali, and sorry for being so strict with time. We will now move on to our second speaker. We have Professor Robin R. Murphy. Dr. Ron Murphy is the Raytheon Professor of Computer Science and Engineering at Texas A&M University and founding director of the Center for Robotic Assisted Research and Rescue and an ACMIE and IEE Fellow. She helped create the fields of disaster robotics and human-robot interaction, deploying robots to 31 disasters in 5 countries, including the 9/11 World Trade Center, Hurricanes Katrina, Harvey, and Michael, and the Kilo volcanic eruption. Murphy is a multi-award winning researcher. For instance, her contribution to robotics have earned her a U.S. Air Force Exemplary Civilian Award Medal and the Motorio Kizuo Award for Rescue Engineering Education. Thank you so much for joining us, Professor. Over to you.
Well, thank you very much for having me. And my apologies for the Murphy's Law. I'm sure you're all familiar about Murphy's Law. That sort of lives that. What I want to talk to you today is about robotics in general for disaster management, and really appreciate the great talk from Dr. Aga. Could you advance the next slide? Thank you. A little bit about me. I think the big thing I would like for you, there are 5 things, maybe 2, 5 plus or minus 2 things I'd love for you to remember from this talk. And one of them is that the Center for Robot Assisted Search and Rescue, we really focus on emergency managers and government agencies during the response phase primarily, but also preparedness and recovery. And we've worked in, we've deployed to disasters in 5 countries and have trained over 36 agencies in 20 countries. Next slide. So the second thing I want you to remember is that disaster robots don't look like the ones in movies, and they don't look like the ones in most competitions, not even the ones you just saw for the DARPA Sub-T, Subterranean Challenge. Next slide. Robots can be ground, aerial, or marine systems. So the ground robots that have been used today are typically very, very small. You see that snake robot that was used at the Mexico City earthquake. You see an Anukdan, that category of small robot, about the size of a shoebox, is what's typically used at building collapses, from World Trade Center to things like the Surfside building collapse. What you want are small robots that can go into spaces that people can't fit. So again, the Sub-T is wonderful for, we saw Fukushima, I was part of the team there. That is a human habitable space. There was a lot more room to get to, just people can't get through. These are the ones that we're seeing the big advantage because most robots can't move as fast and see as much as a person. So we don't use them to substitute for people. Likewise, these small, inexpensive aerial systems that fit in backpacks that are easy to carry. And the same thing we see with the underwater and the marine surface vehicles, robot boats. Okay, so those are, you see ROVs and kayak-based boats. Next slide. The third thing I would like for you to remember is that robots have already been used for almost every disaster and every mission objective. A big thing about what we have found in our studies of innovation is that it's a demand pull, not an innovation push. The responders know what they need. And so it's a matter of getting it to them. But if you look, we've seen robots are used extensively for the world's #1 disaster, which is flooding. Earthquakes, tsunamis, wildfires, hurricanes, tornadoes, volcanic eruptions, nuclear accidents, Fukushima, major use, marine casualty events, such as helping lifeguards with the Syrian refugees coming across to Greece. That's probably one you didn't think of. Building collapses, chemical spills, and pandemics. So let's go to the next slide. Now, let's just think about that. Pandemics, that sounds weird, right? When we think of disasters, but we're thinking of this all hazards approach. The emergency managers consider pandemics just one more type of disasters. And if you see that in the first year, from the very first use of a robot for COVID we saw 338 instances in 48 countries. Next slide. And look at these. These are for very distinct uses. So public safety was the leading use. They were using a lot of UAVs to disinfect. They're using agricultural sprayers to spray areas with disinfectant, or to help with quarantine. Clinical care, disinfecting robots. Work and education using telepresence. We saw a lot of delivery robots helping people out, and a lot of work in laboratory and supply chain automation for the medical profession. And we also saw some important things of helping quarantine camps, or just helping people in nursing homes at risk. Next slide. So robots have been used for almost everything already, and that remembers not just for the immediate response, but for all phases. So when you think about the before an incident happens, for instance, like a flood, being able to map your land use, to get that digital elevation work, to monitor the rising waters of a flood, to document your infrastructure, what are your vulnerable businesses. And of course, during a response, there's tactical, those life-saving operations, where it's literally helping the responders. You're not automating that, you're assisting them to see how to best get a boat in the water to get over to that house, to get that person off of it. Reopening ports and infrastructure, big problem with the tsunami in Japan, took out all of their bridges for their trains, and all of the ports, which you would normally bring in, like you saw with the Haiti earthquake, you're bringing in the majority of your supplies on ships, but you can't tell if they're fixing to run aground. Likewise, recovery, being able to get that comprehensive damage assessment, again, to monitor what's going on and document those states. Next slide. So the fifth lesson, and I think this is really important, is that what we're seeing is that less developed countries can adopt. This is not something that is rocket science. I mean, even though we've got brilliant researchers like JPL that are working on the next area, but the majority of robots that have been used, the aerial systems that have been used in major disasters, are a $1,000 DJI Mavic Pro series, not the $40,000 ones with LiDAR and all of that. They're using AI structure for motion. Anything you can do with that $40,000 one, you can do with that $1,000 one, and you can carry it in a backpack. And if you lose $1,000, that's fine. And so that 3D reconstruction you see there of the Surfside collapse, and you can zoom in, and it's about 4 centimeters of accuracy, was done with the DJI Mavic over about a period of 2 hours of flights. So that gives you an idea of what you can do. Next slide. So I said I would like you to remember 5 things, but maybe if you just remember 2. And the first biggest one to remember is that robotics are within the reach of emergency management agencies in any country. They're not that expensive anymore. They're not that hard to use. And the second thing is anything we can do, the Center for Robot Assisted Search and Rescue, anything I can do to help advise, to support a deployment, we do anything at no cost. We have a large set of best practices and training modules. Whatever we can do to help, there we are.
Thank you so much, Robin. I know the time was limited, but you managed to put everything in 10 minutes. Thank you very much. Please don't forget to add your questions in the chat. We will now move on to our third speaker, Mrs. Paige Day. Paige is the Director of Sales for Hydronetics, the creator of Emily Robotic Rescue Boat. Having worked in public safety for over 20 years, she has been able to transition her skill into the field of robotic technology by incorporating this into rescue and recovery efforts. As the Director of Sales for the innovative company, Hydronetics, she has used her career experience to integrate this technology and assist them with rescue, life safety, and scene stabilization, with the focus of keeping both the rescuer and the victim safe. Paige, thank you for joining us. The floor is yours.
Hi, good morning. Can you hear me okay?
Yes, we can hear you.
Okay, excellent. I'm actually in the field today assisting the state of Ohio with a recovery effort. So I appreciate this, and I'm so happy we have the technology that I can go ahead and join this meeting. So good morning, everyone. My name is Paige Day, and I'm going to talk to you about the Emily Rescue robots platforms and the way that Hydronetics is integrating new technology to assist with search and recovery efforts globally. Next slide, please. This is just a slide talking about the genesis of the Emily program. We've been working with Dr. Murphy since the beginning. And this is just how the robotic platform of the Emily has changed and how we've used feedback from other agencies to make everything better, stronger, and user-friendly. Next slide. So the first one, this is the basic Emily. This is how it started. Dr. Murphy discussed using this in the Mediterranean Sea, rescuing people. This little robot has the ability to go out and hold multiple people and keep afloat until the rescuer can determine what's the best way to get them out of the water. Next slide. It's easily deployable. All of our the composites that are made with this robot is aircraft grade fiberglass, epoxy, and Kevlar, so it's very strong, easy to deploy, very lightweight, and battery powered. Next slide. This is the sonar Emily. This was the next platform that was used. This was actually on a recovery effort that I was on way up in Arizona. As you can see, the platform's very small. It enables people to go in and see what's going on under the water, whether it's brackish, salt, fresh, etc. It's very portable, battery powered, easy to set up. This system was actually used post-disaster from Hurricane Dorian to clear the ports to let the big ships get in with humanitarian aid. Next slide. This is the Sonar Emily with the post-processing software. This is just the information. It's basically a hummingbird system, which is excellent because first responders get it. So it's not complicated, it's easy to use, it's real-time transmission, and it's also easy to post-process for documentation purposes. Next slide. And this was actually on a, just so you can see real-time, we were able to identify a target of a missing person that was missing for 2.5 months with the sonar technology. And the little Emily, we were able to find him in 2 hours. Next slide. So we talked, this is just easily how it's ran. You can run it from one person, or you can use 2 people to run it. So we talked briefly about the Emily. That's the original product from Hydronaulics. Now we're going to talk about the new technology that we're integrating into our platforms. The first one is the Speedo. It's a water sampling system. It enables you to go out and get water samples autonomously, and it draws the sample, brings it back for analysis. It gives a real-time stamp, also the GPS location. This is being used in France right now. They had a big problem with dumping from cruise ships, dumping waste into the water, and the scientists are able to use this and actually qualify their samples and justify that the cruise ships are not doing what they're supposed to. And environmentally, that's very important. Next slide. So this is, again, talking about the environmental response. We all know what's going on with our waters. It's very important that we are able to identify not only fouled samples, but also determine what's the best way to clean up our waterways. Next slide, please. This is the newest drone that we've come up with. It has a 360 sonar on it, and it's able to, for post-disaster, go over, get a quick look, can jump over dams, fly over where waterways, and be able to give real-time data, sonar data, back to the first responder so they can determine what's going on. This is going to be very beneficial, like what happened in Michigan 2 years ago when all the dams broke. This can really give valuable information to engineers so they can determine what's the best course of action to start reconstruction. Next slide. And again, it uses the same payload station as the Sonar Emily, so it's very easy to use. It has the same Hummingbird sonar, but it is the 360. Next slide. Okay, this is the aerial real time. In the instance of time, I just won't take too much time on that. So next slide. These, I know Dr. Murphy discussed this as well. These are our new disposable drones. The one is called the Crow. This is for military. The second one is the Dove, which we'll see the next picture. It's white. They have a very small payload. They're designed to just have one easy course. The price point is under $1,000. They're considered disposable, super easy to use, super easy to deploy. You just use your smartphone or tablet and you can deploy medication, water, IV bags, anything that you need. This could have been super beneficial, especially post-hurricane in Haiti, just to get from point A to point Z to a landing zone so people can get the support that they need. Next slide. Oh, okay, so that is the presentation. I apologize that for my lack of professionalism, but I was called out to help Ohio Department of Transportation and the fire department here at Loveland, Ohio. So it's great that I could be with you, and I appreciate everyone's time, and I look forward to talking to anybody that has any questions about our amazing robots.
Thank you so much, Paige, for that presentation. I will now move on to our first speaker, Mr. Gordon Pazer. Gordon is the Business Development Manager at Dorking. He's also the President of the Matic Innovation Council for Security in the Republic of Croatia and Vice President of Croatian Defense Industry Cluster. At Dorking, he gained extensive business development, project and program management experience in business to business and business to government in the UGV sector, primarily in emergency response, humanitarian demining, and counterterrorism program. Thank you so much, Gordon, for joining us. I will now pass on the stage to you.
Thank you very much. Thank you for having me, and congrats to the presenters. I witnessed really beautiful presentations with a lot of things that we are able to learn from. Can I ask for the next slide, please? Okay, so basically, I'm working for the company Docking. We are solution providers of unmanned ground system for special purposes on a global market. Basically, we are in the field for last 30 years. The deployment of over 400 units, 400 robotic systems, different ones, to almost 40 countries around the world. Basically, all of our products are based on the innovations and new technologies. So basically, we are flirting with different areas of use. We are flirting with the different technologies like electric propulsion system, hybrid propulsion system, and diesel-driven type of the systems. So this gives us the advantages towards the different type of the applications. Please, next slide. So basically, we are working in the 4 main areas of use. These are the humanitarian, the mining, and we originated from this field. So for the last 30 years, we are providing solutions for the humanitarian, the mining, and our platforms are ranging from 2 tons up to 22 tons. And basically, they are and we learned a lot for the disaster management from this field, because we learned how to deal with the extreme environments, extreme dust, extreme particles that are flying around, flying debris that are usually present during the emergency response. And basically from that, we moved to the underground mining sector, which is also represented in the presentation from Dr. Ali. Basically, underground mining is also extreme environment in which you need to find the way how to operate with the existing comms and an existing and in really harsh environment. So basically, we used all these experiences to provide the solutions for 2 different other programs that we entered since 2013. This is the emergency response. And the emergency response, we are providing different type of the solutions, so let's say complete solutions for the emergency response that consists of robotic systems, a small one and the big one, aerial system, and the command and control solution, which enables the rapid responders to react properly. So basically, that gave us the important experience to go into another programs, which is counterterrorism, which is even the most demanding environment, because there is people working around the machinery that could be either unmanned or man-driven. Next slide, please. As you can see here, so basically this is the entire UGV portfolio that we are providing. Different type of the products. The top products are for the humanitarian, the mining, while the lower products are either for the underground mining or for the emergency response. Next slide, please. Since the topic of this presentation is the emergency response, basically the systems that we are providing are bigger in size. Because we found out from our end users that they are usually demanding bigger systems that are able to have the capabilities for the survey and reconnaissance, and to have at the same time obstacle removal on the path of intervention. And they were asking for this type of the different capabilities, so they are able either to provide the firefighting or the contamination asset. And these systems can be used in rescue operations in terms of punching through the wall and support search and rescue operations and to move and manipulate the objects. Equally important is the CBRNE and hazmat operations, hazardous material. So you are able to provide the information to the end users, such as levels of oxygen, temperature, different type of the chemical information, whether there is toxic industrial chemicals around or not, for example. And of course, it's always a problem with the logistics. So they need to have like some form of the muscles on the ground. So the bigger robotics are able to provide that as well. So the applications in which usually our users were using these machines are usually at the unplanned explosions at the munition sites or shooting ranges where they induced the fire with a live munition, and they didn't know how to approach the area with the conventional means. The same happens with the flammable material warehouses or oil refineries, chemical plants and warehouses as well. And we learned a lot from the Fukushima event, where they needed to have the system which is robust and big enough to clear the debris and obstacles, so the other intervention vehicles can go through. Please, next slide. So this is a short video from the real case operation. Is it working? Oh, okay. So basically, this is a landfill fire hazmat operation. Basically, they were using the system to extinguish pockets of fire, which were filled at some points with the methane, and the toxicity of the environment was a big one. And I would like to mention here that, as you can see, that there is a lot of smoke, a lot of fire, a lot of particles around the machine. So the sensors that are required for the autonomy here wouldn't work. So I think that there is a long way to go to have maybe in this type of the environment artificial functions, let's say autonomous functions. So basically, you need to have like a reliable comms mesh network, and to have the possibility to operate in this type of the environment, and to have manned supervision over the applications of robots. Next slide, please. So basically, the limitations that emergency responders are usually having. It should be assumed that the staff have no precise knowledge of the actual situation, and they need to use this type of the systems, either a big one or a small one, to understand the situation, so they don't make an incorrect assessment. And unsuccessful execution of accident management and mitigation measures could have catastrophic consequences for human lives. I think that happened in Tianjin case, where they had the incorrect assessment of the situation and they send the people to the wrong environment, let's say. Next slide, please. So the emergency response limitations is that because you have a situation where the humans are not able to go, it's much easier to send the asset like a robotic system in order to have the possibility to react in terms of there is no human restrictions on entering dangerous areas like you see on these pictures. So you are able to go faster because you are able to approach operational area without special way of preparation. So you can have the longer and more durable operations because there is no limitation due to the personnel protective equipment, for example. It's safer because you are putting the humans out of the harm's way. And of course, with this type of the systems, you are versatile because you have the wide range of cameras, sensors, and detectors, and with the fewer errors, the people are not exposed to the stress that much like the rapid responders that are in immediate threat. And of course, if you have the system bigger system, you are able to have modularity, and you are able to have the front and rear tool attachments that are able to be used in different type of the applications. Next slide, please. So basically, the entire approach is dirty, dull, and dangerous work, and different type of the tasks and missions could have, and you need to have the asset that is able to provide different type of the tasks and missions for it. For example, reconnaissance and survey task, which could be perhaps the most difficult and dangerous part of the emergency response. And the hazardous material handling is really time-consuming and efficient destroyer of rapid responders momentum, because you need to deal with the situation and you need to play with the cards that are handed to you. So it's really beneficial to have the robotics in such environments. Next slide, please. So basically, the systems that we are deploying or that we are developing for the emergency response are response to military and terroristic threats, natural and anthropogenic hazards, where the extreme conditions could be anticipated, such as fires, explosions, severe environment, high temperatures, etc. And in that case, we are putting different type of the sensory aspects, so we are able to understand the situation. Next slide, please. And basically to have the eyes, ears, and muscles in this environment. Eyes in terms that we are putting the sensors, video cameras, and different type of the situational awareness tool that you're able to understand the environment in which you are sending the people. Dirty mean in case that you need to provide the asset which is able to be pragmatic in such environment. And muscle and the ears, so you're able to understand the whole thing. And in conclusion, basically the system has been developed for the emergency preparedness, for reconnaissance and information collection, monitoring and data delivery to the higher commands, firefighting in danger areas, especially in extreme environments, obstacle removal on the path of intervention with the front tools. Basically, the system that we are providing are having the different, they are having water sources, so you're able to provide either firefighting or decontamination capabilities, and removal and collection of objects and water supply in critical conditions where there is a need for. Next slide. Thank you.
Thank you so much, Gordon, for the very insightful presentation. And please keep on adding your question and comments in the chat. We will have the Q&A session very soon. Last but not least, we have Mr. Jayakrishnan Trivikanya. Jayakrishnan is the founder and CEO of Asimov Robotics, a company that provides solutions for various requirements in medical and healthcare, space technology, security, banking, retail, and hospitality sectors. JK has over 26 years of industry experience working with robotics and AI, embedded system design, power control, and microprocessor design. He is responsible for the conceptualization and development of multi-service robots, and he has successfully deployed over 200 robots across the world. Thank you so much, JK, for joining us. Over to you.
Hello, am I audible?
Yes, you're audible.
Okay, wonderful. Thank you very much for the introduction, and thank you for inviting me for this wonderful session. So my focus of the presentation today is the role of social and service robots in combating the pandemic. Please go to the next slide. Yeah, we all know that we are living in a connected world, connected by means of travel, transportation, internet, telephone, etc. Fortunately, internet and telephone will not spread virus, but you know that how fast, because of travel and transportation, an epidemic has become pandemic within few months. So today we'll just go through some of the humble efforts done from the side of Asimov Robotics to manage the pandemic situation. Please go to the next slide. Yeah, here actually I'm dealing with, I'm talking about two major, aspects like social behavior and hygiene, logistics and nursing, and assistive systems and mental health. I'm not dealing today because of the limitation of time. We'll see what all. Please go to the next slide. So it started actually long back. In fact, March 2020, we were actually working with another project when Nipah outbreak was there in 2018 in Kerala. So that is the reason we were able to quickly customize the robot for this purpose. We deployed 2 robots in the working space. One is for educating the people because they were really panicked during the initial days and were not having any idea how to protect themselves from getting infected. So we deployed one robot for making them aware of the situation, and the second robot for answering their queries about this pandemic and the precautionary measures. Please play the video, you can see that. This is the first robot. So it is actually loaded with WHO's information, video clippings, sanitizer, dispensing, mask dispensing. And the second robot, well, you can see that in the frame, it's not in this video. It's talking about answering the questions related to the pandemic. I mean, how to protect ourselves from getting infected, yeah. So next is like April, in fact, the year is not correct, 2020 actually. It's a typo mistake. So 2020 April, actually what happened is like we deployed a robot in nearby government hospital. This was actually developed within 15 days. So this robot was a comprehensive solution for dispensing food and medicine inside the COVID ward, and also to do the disinfection of trash. We have to collect trash from the patients also. This was for asymptomatic patients, tested positive patients. So this is to minimize the exposure and the use of PPE kits inside the COVID ward for the healthcare workers. And this robot was also equipped with telemedicine capabilities. Then it was able to do the targeted disinfection in case of any spillage due to vomiting, coughing, or sneezing. You can go to the next slide and play the video. The name of the robot is Karmi Bot.
Hope the boxes are filled. Press the buttons for selecting rooms. Karmi Bot on duty.
You can see what is happening inside through a mobile device. You don't have to control, everything is autonomous. And in case if you want to control, you can take the control. And this is actually, we are not able to, take videos from the hospital. We are not allowed. Doctor. That's why this is a simulated environment, emulated environment. It's our office only. So in the return journey, you can see a black box wherein the patient can put their trashes. So that is UV enabled. So when it is closed, then
UV
the
disinfection started. Please don't open the tray.
And it goes back to the nursing station. And this is the targeted disinfection. You can use either sodium hypochlorite diluted or any other disinfectant. And you can mark this point place in the map, and you can send the robot inside to do the disinfection, first level disinfection. Please go to the next slide. By June 2020, what we did is we started, equipping the robot with COVID screening facilities, wherein we were able to integrate temperature monitoring, then, detection of mask, and then, social distancing, then also providing sanitizer for sanitizing hands, and also gadget disinfection using a UV box. You can go to the next slide. So the same robot by December 2020, we deployed in a polling booth during the local body elections in Kerala. So there, the robot actually screened almost 300 people, voters in queue from morning to evening. And then it took hardly 20 seconds to complete the procedures. You can play the video. initially, because of their seeing the robot for the first time, little bit skeptical, but immediately they were very comfortable operating with the robot, getting screened. The left hand is equipped with the thermal sensor, right hand is with the sanitizer dispenser. Go to the next slide, please. So this is one of the most important use case because we actually are working with one of the reputed hospital group, Narayana Hridayalaya. This use case was actually introduced to us by Sri Dr. Devi Prasad Shetty. He is the chair of Narayana Hridayalaya and one of the world-renowned cardiac surgeon, who is also the award winner of the second highest civilian award of India. So he actually, I mean, the hospital is full of ICU wards, like, at least 30, 40 surgeries happening per day. So the immunity level of the patients who are undergone surgery is very low. And actually they have a kind of staff who are actually called as medical runners, transporting various microbiology samples and clinical consumables back and forth between departments like ICUs, then pharma, store, all these places. So in order to minimize the human presence to safeguard the patients from getting infected, we have deployed a set of robots which are looking like miniaturized ambulances moving through the corridor with these samples and medicine and other consumables. You can play the video. I'm going to show you a video actually from the ICU itself. And this was very challenging situation for us because of the highly dynamic nature inside the ICU. People are actually moving back and forth. The robot is actually taking the sample and it's taking the sample to the laboratory and comes back with the report. So we are getting a lot of imaginary obstacles due to the reflection of the metal cladding. So we have used sensor fusion using almost 6 or 7 different types of sensors in this case. Please go to the next slide. This is the product which we are launching today. So I have changed the launching date to be today because of this presentation. So I'm very happy to officially launch this through this presentation. This is a very cost-effective solution for health screening, which has got temperature sensing, as I told you earlier, oxygen saturation level check, and symptoms check, and ensure the use of mask, and then ensure the social distancing is practiced, and also the sanitizer dispensing. See, one thing which we have noticed is that during this this period, it is practically difficult to adopt expensive robots for countries like us. So this is a very cost-effective solution which can be installed at every doorstep of every organization, and then to screen the visitors and workers. So in any case of that, these visitors are not, passing through this procedures. If anything is found abnormal, then they won't be allowed inside. The door won't be opened, or there is also a barrier. It's an optional. If the door is not automated, that won't be opened. And apart from this, we are also working with a surgical robot for a problem called craniosynostosis, and also for a compliant platform for a neurosurgical laparoscopic neurosurgery to minimize the number of surgeons performing the surgery. That is also very important, but because of time limitation, I cannot show this in this presentation. Thank you very much.
Thank you very much, JK. That was a very great presentation. And I believe that we have some questions in the chat. I see that we already had a discussion going on. Once again, thank you to all the speakers for this high quality presentation. It is now time to move on to the Q&A segment. And for this, I would like to pass the floor to my colleague, Maxime Croft, who is also an intern at the Resilience to Disasters and Conflicts Global Support Branch at INA. Maxime, over to you.
Many thanks, Lamello, and thank you all again to all the speakers for the insightful presentations. In this Q&A session, we will try and answer as many questions as possible in the next 25 minutes. I would like to remind the speakers to turn their cameras on when responding, and I'm checking all the questions that we have. I saw some questions already, however, I encourage the audience to address their doubts and inquiries in the chat box. So let me start with the first question. Which is directed to Robin. Robin, how do you determine which robot should be used after a disaster has happened? Okay, I'm not sure if
Yeah,
Professor.
there we go. I know that. So we do have a procedure for doing that. And it looks at the constraints. I mean, first off, you've got size constraints, like for a mine collapse. If there's a lot of methane, you have to use what's called an intrinsically safe device. You've got all of these sorts of things. What we find, though, the big determinant, particularly with unmanned aerial systems, is cost and logistics. Is that you want to use the least expensive system you can. Makes sense because you're always at risk. And you want to use one that's easy to carry, because if you're taking these out to the field during a disaster, you don't have a lot of power, right? So you have to be able to recharge something off of a car battery versus bringing a generator. So you have to think about that. If something goes wrong, you need a backup. So we tell people when you go out to the field with one robot, you should go with 3. You can always keep 2 and one after the other, and you can have spare parts, but you always want to use ones that you can recharge the batteries, because the batteries tend to be the heavy part, right? And then trying to carry and push this into an SUV or put it into a backpack, that's a problem. So those are the big ones, but we have a detailed procedure list, a checklist to do.
Thank you a lot for explaining that. We have another question, and that one is directed to Ali. Dr. Ali, what are the main advantages and disadvantages of the different types of robots you use?
Okay, so the question is, what are the advantages and disadvantages of different types of robots? Yeah, so I think, you know, as Dr. Murphy already covered that well, it really depends on the mission, but you know, you have ground robots and aerial platforms in the first division of you know the robot body, and the main advantage of aerial systems is like very quick. You can cover a large space, gather the necessary immediate information, you know, for certain strategic decision making. Then in the next step, maybe when it comes to carrying a certain type of payload, if it's needed by the mission, or manipulating the environment and changing, you might need to have ground robots that are going in, interacting with the environment, or going into certain, you know, narrow passages that might not be feasible for aerial systems. Or they can potentially act as repeaters, so that if you have an aerial system further down into the course, basically you have a ground robot that is dropping repeaters along the way, so that you communicate constantly with your aerial system. So that's where kind of different benefits that can come from a ground robot system. And within the ground robot system, of course, there are different modalities. You have legged platforms for very, you know, challenging terrain. You have wheeled systems just to carry the payload up to, you know, the places that are flat. But yeah, in general, if the operation, it's possible for the operation to have this heterogeneous team of robots, similar to a human team, which has different set of skills, that would, you know, allow a higher variety in the concept of operation.
Thanks a lot for explaining that. The next question is for Paige, and the question is, what has been the biggest challenge on the deployments you have made so far?
Well, that's a good question. Obviously, environmental is always an issue. Just you have to be prepared for the type of weather that you're going into. I work off the water, obviously, so sometimes that's a challenge. Access can be a problem. We've developed different ways of carrying the equipment in. I know Dr. Murphy was discussing that. You always need extra batteries, which can be challenging as well. So you have to consider all of that and pre-plan. I have a list that we operate off before we go out to assist with operations post-disaster or just helping people with search and recovery efforts. I lost you, sorry. So those are the main challenges, but I think the key to overcoming any challenge is preparedness. And that's where we all are in, especially with emergency management, is you have to be prepared and be ready to deploy at any time.
Thank you so much for answering that question. The next question I have is directed to Gordon. Which kind of data can be retrieved from the robots when it's used for fire extinguishment?
Okay, it's a good question because it provides the information to our rapid responders. I mean, to the end users. So basically, the systems that we are deploying usually have these certain set of sensors and detectors on board. The payload of the system is enough to provide such an information. As a standard one, we are putting the oxygen level, temperature level, and toxic industrial chemicals. We are able to add, and we are adding the GPS and the chemical warfare agent detector in some cases, and radiation detector. So basically all this information are distributed to the operators, and from the operator place we are able to distribute this information to higher commands depending on the communications that we have available. So yeah, so this can be expanded and added different type of the mission specific sensors, but these are the basic ones.
Thank you. JK, we have a question about the use of the face masks. How does the robot respond if someone is considered not to be wearing a face mask or is not wearing it properly?
Yes, in fact, we have trained the model with all different types of masks available here, with the different lightings and different color patterns. I mean, different variety of different geometries we have trained. So we can understand that if the mask is not properly worn, in case of it is just put underneath the nose or anything, the robot will advise the visitor to keep it properly, wear it properly. So that's there.
Thank you for answering that. The next question is coming from Mike Malango. And the question is directed to Robin. And the question is it common to use DJI drones since there are embargoes around Chinese technologies?
It is common. I mean, DJI has something like 87%, the numbers vary, of the entire market. So it's very common to use DJI products. It is now a problem in the United States, though. I can't speak for other countries to use them. For example, Florida, the state of Florida says in 18 months, all Chinese-made unmanned aerial systems, use of that must be discontinued by any of their agencies. So the robots, these UAVs that were spectacular, that had huge success at Surfside, that changed things that were taking 3 days into 3 hours or less, that enabled this, will not be used. The problem is we don't have any other replacements. And I think that, as you saw with Dr. Jagakrishna's talk, user interfaces, there's a lot to developing robots. There's the platform, there's the usability of it, then there's how it fits into that workflow and process. And we don't have any technology that's really comparable in performance, reliability, usability, and cost in unmanned aerial systems to the DJI models right now. and we'll see how that turns out.
Thank you so much. The next question is for Dr. Ali again. Ali, how do you see the future of your team and the Nebula autonomy solution after the DARPA subterranean challenge?
Yeah, so definitely we are trying to learn a lot here and understand how these technologies can be used for good, and we can expand their applications. We have already been trying to expand our autonomy AI solution to multiple other projects within JPL with other sponsors, including NIOSH in the mining sector. But the idea is to develop our AI solution, we call it Nebula, in a platform agnostic form. So at the moment, as I showed, the same autonomy goes on legged robot, wheeled, or drone. And we are trying to make it as modular as possible so that as we learn more and as we see, okay, this is what the experts in the domain actually believe would be the best robot, how we can help them by making it a bit more autonomous, a bit more intuitive for the user, and maybe most importantly, make the operation scale larger, right? For example, focusing on drone, it would be much nicer if you can press a button and 5 of them flies at the same time with the same cognitive load to the operator today when the operator flies 1 robot, right? So that's the kind of the first baby step here before full autonomy. Of course, they're going towards assistive autonomy. But yeah, the goal is we are basically, our team is pretty passionate to in expanding the technologies and using them in disaster response.
Thank you. Paige, what are some of the future features or challenges you need to work on to make your robots more efficient?
Well, the Emily robot right now, I think the main focus was operations, actually using it, because a lot of times in engineering, we don't make the connections as robust as they need to so they can withstand the challenges that are in the field. So we've been working through that, and and obviously batteries are always a weak point as well. You want to make sure that you have the best possible battery for the robotic operation. But I think the main challenge was just identifying that you can't have it be so fragile. It needs to be able to withstand not only the environment, but also the end user, how they use that. As far as the new little drones, they're awesome because they only have one mission. They're not that complicated. That's why they're not that expensive. So I think we're really going to see that having a cache of them, if you will, that are easily deployable to offer sustainability to people that are in crisis post-disaster.
Thank you. We have a question coming from Melvin Manuel to Robin, and the question is, what are the communication technologies used in SAR robots?
For ground robots, I am unaware of any disaster where they didn't default back to some type of tether. So they're using usually fiber optics. So at Fukushima, they wound up putting fiber optics on those Solums, Talons, and iRobot PackBots to get in there. For the really smaller ones, when you're trying to get inside rubble, you're also using a tether. Part of it is because these void spaces are not flat. It's not human habitable. It's been deconstructed. You're usually having a high vertical component. So essentially in portions, you're rappelling down. So you need a belay line. If you're starting to put a belay line on it, you might as well put your communications through it. And by the way, a ground robot going into rubble has got a time of hours. One of our missions was about, I think, 26 hours at the Crandall Canyon mine collapse, where we literally just stopped it, changed out car batteries to power it, kept on, and then we had to take a break. We had to get a little sleep cycle. We couldn't run. We were all cognitively fatigued and tried it again. So these are some of the things for ground robots to think about. The aerial vehicles, of course, use wireless. And those are what we typically see is that we're using the public bands, the 802.11, the 2.4 gigahertz, because that is commercial off the shelf. That's easy to do. Trying to get a public safety spectrum that's generalizable across the world is typically very difficult. So hopefully that helps.
Yes, it definitely helps. Thanks a lot. I think we have one more question left before wrapping up the session. And this is a question to Gordon. In which kind of disasters are the robots the most useful?
Hello. Yeah, so basically the most use case scenarios where our robots were used are for the unplanned explosions at the munition sites. Basically, when the munition site caught on fire, it creates far greater danger. Our robotics are more for the national level, not for the, let's say, firefighting level. So basically, they are deploying them in this type of disasters. We have several use cases in the chemical plants and in landfills. Basically, for all hazmat operations that requires bigger machines that are able to remove rubbles in front and create a safe path for other intervention vehicles. So basically, in all disasters where they are requiring the modular system that is capable of providing safe access to other intervention teams.
Thank you. Well, in the interest of time, I would now have to put an end to this Q&A session. Thank you very much, everyone, for taking the time to attend the session, both the speakers and the attendees. It was a very productive discussion, and it was so nice to hear of so many examples where robotics have been used in disaster response and management. Before we close today's session, we would like to remind all of you that our next webinar will take place on the 28th of September, and it will focus on artificial intelligence in disaster management. The timing is the same as the one we had today, 3 p.m. Central European Summer Time. See you in 2 weeks, and a good day to everyone.
Thank you.